Okay, good morning. Well, so we start discussing, approaching, so to say, the machine learning and clustering algorithms. These algorithms and these actually all machine learning methods based on an assumption that there is some geometry in the data, hidden in the data. So we can measure distances between points, data elements, and using these distances, we might get some points close to each other with respect to the given distances, to the given distance. So we could consider some points close, other points are far from each other. So we can perform clustering, collecting all points, all close enough points, assuming that they are of the same mold. So the most weak point of this strategy is a distance. What is a distance? In many cases, well, in probably 90% of cases, people from computer science, they usually don't think about a distance. They believe they have a Euclidean distance everywhere. And therefore, there might be many mistakes in their works. Actually, their papers, most of their papers are based on the idea that they might calculate Euclidean distance between fuel consumption and salary, or something like that. They don't pay attention to this fact. So for the moment, we even don't, when we got complaints about problems with results of some data analysis or machine learning or neural networks, we don't know precisely. Was it because of weakness of the algorithms or because of erroneous data pre-processing? And therefore, the most important point, first step, is how to introduce a distance, properly introduce a distance, a proper distance which would fit the nature of the data. And that is why actually we need data models, graphs as a data model, because graph itself, graph structure, this set of nodes connected with edges, can provide us with numerous distances. And I'm going to spend a couple of lectures describing you the major principles, how to construct distances whenever you have a graph model of data, and how you could estimate, in particular, the information value of the data, how computer can estimate the information value of the data based on the graph theoretic model. Whenever you have structure, you have some information. If you believe that data has a meaning, this data pool has a meaning, it should be somehow reflected in the structure of this database. Unfortunately, on the most of mathematics department in the world, graph theory is still taught on the level of 18th century. And we all know that this shit is good for nothing. The modern developments of graph theory are related to algebra. There is algebraic graph theory. It's something which allows us to work with larger scale graphs without spending much time counting node by node. So I'm just going to introduce you into a modern graph theory within, say, 1 hour or 2 hours, basically, okay? First, indeed, between the mindset of the 18th century what you probably, when you open the graph theory book, or you probably had some couple of sections or even a chapter in some elementary mathematical course about graph theory. So there should be somehow a bridge between 18th century mindset and linear algebra stuff. This bridge is provided by the book I sent you last Friday. Okay, so it's just a book from Finland, graph theory, translated into English, and it gives you basically the ideas about how to translate graphs to matrices. I will assume that you already understand that any graph, we already mentioned it several times, that any graph, and in particular even simplicial complexes, could be described in terms of adjacency matrices. Okay, so I suppose that an adjacency matrix is given. But, well, please have a look. So this is just a best, from my point of view, the best translation from graph mindset, complexes of nodes and edges, into some linear algebra stuff. And I will start already with some linear algebra. Okay, so we just work with certain types of matrices. Graphs are some matrices for us. And indeed, this is it's quite clear from the data analysis point of view, because any matrix is a kind of a relational database, and vice versa. A relational database is a matrix or a graph. So we should learn how to construct, how to relate nodes if they are connected by some set of vertices. In real life, in usual geometry, there is no such problem. If I have some kind of I don't know, meter or scale, I could just measure any distance. Okay, and there is no big problem. I just can use laser, for instance. Okay, we are in Euclidean space, but if I remember that I'm not able to jump through the rows, then I should search for some other path. Okay, for instance, to reach you on the very last row, I should search for some path. And moreover, yes, in this particular situation, indeed, this is a unique path. But in principle, there might be many paths. How to introduce a geometry? What is the distance then? I can go this way, I can go that way. Okay, so basically these are the major answers for, major questions for algebraic graph theory. Now, I stop sharing the book and I start sharing the presentation. So this presentation I send you to, okay, slideshow from the current slide. And display setting, duplicate slides show. Now you should, yes. Well, we discussed last time that there might be many matrices which we could use to characterize a graph. Adjacency matrix of zeros and ones. One if there is a connection, edge between nodes, zero otherwise. Laplacian matrix, a little bit linearly modified adjacency matrix, okay? Well, if graph is regular, no much difference between these matrices. If not, well, a spectrum is a little bit shifted, but the properties are more or less the same. Okay, so adjacency matrix 0, 1s, Laplacian matrix. I sum all elements in rows of the adjacency matrix, put them on the major diagonal, and set the adjacency matrix with negative elements outside the major diagonal. Okay, so this is a Laplace matrix, Laplacian operator. Laplace matrix, Laplacian operator describes a diffusion. The solutions for the equation, for the matrix equation, or if I think in terms of partial differential equation, solutions are called harmonic functions. Okay, now eigenvalues, eigenvectors. if I take an adjacency matrix, well, I order all eigenvalues in their natural order. They are real. If the matrix is symmetric, graph is non-directed, then all eigenvalues are real. I can find the biggest and I can find the smallest one. Sum of all eigenvalues are called the trace of the matrix. So if I have, basically, if the graph is simple, the sum of all diagonal elements would give me 0. If the graph is simple, like here, simple graph means that there is no self loop. I have on the major diagonal all zeros, and it means that the trace is 0. Trace is also 0 in this case. Eigenvalues of the Laplace operator, the minimum eigenvalue is 0, maximum depends. In the normalized case of function normalized Laplace operators, the maximum eigenvalue is 2. So in between 0 and 2, okay. Largest eigenvalue. So this is how computers calculate numerically the largest eigenvalue. We know so far that maximum eigenvalue of the adjacency matrix is related to the degree of the node. Degree of the node means how many neighbors a node has. So there is a maximum degree of a node and average degree of a node. It's possible to show that the maximum eigenvalue of the adjacency matrix lays somewhere in between these two values. It might coincide with one of them, but that's all is known today. It somehow depends upon the structure. And it could be bounded from below by the average degree and from above by the maximum degree of in the graph. Okay. Another inequality which is known is that it's bounded by the square root of the maximum degree and from below and by maximum degree from above. If graph is regular or all nodes have the same degree, okay, regular graph means it's a lattice, like a lattice. Every node of a lattice has the same number of degrees. For neighbors, depending actually upon the dimensionality of space we think about. Okay, in this case, maximum eigenvalue is just the d. It's just the degree of the node itself. Now, there is a big topic about spectral drawing. People take, okay, suppose we have an adjacency matrix. People take 2 or 3 major eigenvalues of an adjacency matrix, take the corresponding eigenvectors, and consider the elements of eigenvectors corresponding to every node as a coordinate, or as 3 coordinates, for instance, of a given point in the point in space. Then they connect points if they are really connected in reality in the graph. And they have something what they call a spectral drawing. Sometimes it's useful because it helps. For instance, this is the example of, I guess not all streets in Rome. Rome is a very big city. Well, but you know, probably a central part of the cities of Rome. If streets are connected, each street is a node if they are connected, crossing each other. They have a common crossroad, then they assume to be connected. Okay, so it's then we have a graph and we can draw it. In principle, spectral drawing is useful sometimes because it helps to identify some structures or, you know, part of the network created with a particular rationalities. In case of Rome, I wouldn't say that this is the best example, since Rome had been reconstructed, redeveloped many times during the history, completely destroyed and reconstructed again and again. So what we see here is a mixture of different epochs and, you know, a fingerprint of thousands of people basically, or thousands of cities existing on the place of Rome. Okay, so but nevertheless, sometimes it's useful. If there are just few steps, for instance, it's possible to identify places with different actually urbanistic style, different architectural approaches. It's possible to identify ghettos. For instance, historic ghettos could be immediately shown because they are isolated, so they would be somehow isolated within a graph and so on. So spectral drawing is very useful. This is an application of this eigenvalues and eigenvectors. Okay. Now, the problem with graphs is that they might have different isomorphisms and automorphisms. We don't know how to draw them properly. And this is a problem of data interpretation first. And this is also a problem of data visualization. Whatever data and data pool you have, you should be able to sell it to customer, right? So to sell it to customer, it should be properly drawn. How? So what we will learn today is that this drawing, I mean efficient drawing, is based on the eigenvectors. So it's a spectral drawing, eigenvectors of a graph matrix, right? But not all eigenvectors work equally well. Actually, because we like symmetries. So probably those eigenvectors which are responsible for those symmetries, okay, might be most efficient. We know these, I mean, this knowledge is very intuitive. You will see that in particular, what we consider as a standard geometry, you know, with drawing of the squares, solid bodies, whatever, in fact, it's just representation of particular graphs with respect to their automorphisms, eigenvectors responsible for their automorphisms, symmetries. Okay, people like symmetries, and it helps us. Whenever you draw something, try to find symmetries and representation, I mean, of the database or a graph accordingly the symmetries. Okay, so this I'm just trying to give you some, you know, at least a perspective of what we are talking about. First idea is a graph is could be considered as a set of walks or paths. Okay, so it's just a sequences of nodes. They might be open, they might be closed. If they are closed, they are called cycles. In fact, whenever we consider a matrix, adjacency matrix, it contains the whole information about graph. You can calculate all set of cycles, nodes, and so on. So this is the idea. The major property of the adjacency matrix is that if I take, well, a kth or power of the adjacency matrix, okay, so just look here. So k power of an adjacency matrix, the element ij of a in power of k gives me the number of paths or walks existent between nodes I and j of length k. So this is the major property. It is probably you already heard about it. If I have an adjacency matrix and I need to know how many paths existed between I and j, two nodes of length k, what should I do? I should multiply the matrix A by itself k times, and now I have a new matrix A in power of k. I take the element ij, and it counts me all paths existent between I and j of length n. If I need length n plus 1, I multiply A in power of n by A again, and look at the element ij. The proof is given by induction, basically. And personally, when I teach this induction method in real analysis, I just introduce this problem. because it is the most useful, I guess. Well, concerning walks, walks might be also considered as an algebraic object. We can concatenate them, okay, connect one path and one walk with another walk and have, how to say, a combined walk. We can find a reverse walk. Okay, maybe I just close the door. Just a second, I close the door because we have a fest here. I don't know. Yes, I'm back. Right, so there might be a reverse walk, just walk made in the opposite direction, and identity element, a node itself. So summarizing these three properties is how to combine elements, how to inverse element, and what is a unit element, gives me an object which is called a group. Walks form a group. It's an algebraic object. Our numbers, you remember maybe in real analysis, you should discuss that what we know as numbers, real numbers, form a field. They have two operations and so on, but more simpler, I mean, a simpler object is algebraic object is a group. So walks form a group. Now, if I take an nth order of the adjacency matrix, sum it over all j's at which a path starting from I can end, I get the nth order degree of the node I. It's just the number of available paths available from I. The first order degree is what you study in school, in the graph theory. So it's just number of neighbors. If you multiply A in adjacency matrix in power of n, you take the number, you can obtain number of neighbors on the distance n. Okay? This is a result. Now, indeed, we suppose that degree of zeroth order degree of the node itself, so a neighbor of zeroth order of a node itself, it's the node itself. So its degree is 1. And then graph forms a dynamical system. If I have, so dynamical system is just described here. The property that I can calculate, I can count the number of paths existing between I and j of length n could be described by this equation. So I have a vector of all nodes of which each element gives me, if ith element gives me the number of walks available from node I of length n. So if I take this vector comprising of all these elements, multiply it by a, I give another vector. And this new vector gives me, each element is now the number of paths of length n plus 1 available from I. So whenever you have a graph, you have a dynamical system which shows how the number of paths are accumulated by every node in the graph. Okay, maybe it sounds a little bit dull, but that is how we reconstruct then geometry. It's a little bit more tricky and complicated than a usual geometry in school. But you know, for usual geometry in school, now it sounds very simple to us because we used to this theory for centuries. Since Egyptian time, for 3,000 years, we learned how measured distances. Now it sounds to us very simple. Here we don't have such a luxury as continuous isotropic space. graph provides you different path and at different distances. Okay, so we should develop a little bit more subtle tools to develop a geometry and distances. Okay, now, yes, well, what if we now, what algebra could tell us about an adjacency matrix? I can use, first of all, I can use the eigendecomposition of the adjacency matrix, of the case power of an adjacency matrix. If I have an eigendecomposition of a matrix, in order to calculate the kth power of the matrix, I simply can calculate the kth power of eigenvalues. Eigenvectors are the same. This is a great simplification. In fact, in order to count long distance neighbors, numbers of long distance neighbors, numbers of walks, numbers of cycles, I need only no eigenvalues, nothing more. I can forget about all these metrics. I simply calculate these vectors, eigenvectors, and now I work with eigenvalues. So for instance, number of all walks of length n in the graph G, okay, so I take a in power of n, ij elements, okay, and then I sum over all I and j. If I plug my eigendecomposition here, I can calculate it. So it's just the eigenvalues of matrix A in power of n, and there is some constant coefficient. Okay, so it's a little bit, you know, we used to work with numbers, not with matrices. Okay, so eigenvalues and eigenproperties, eigenvalues, eigenvectors is the tool how to get back to the earth, to something we really know how to work with. People indeed, I mean, in mathematics, they do not work with formulas like that. This is very good for showing students, but in reality, people work with generating functions. They create such functions which has the following property with some auxiliary parameter t, which have the following property. If I need some quantity at for the order of n, I should calculate the nth order derivative of the function, of the generating function. So this is a standard tool in mathematics. Don't be scared. Maybe this is the most couple of, there will be most so mathematically overloaded lectures in the whole course. Okay. Now, number of closed walks. These are traces of the powers of adjacency matrix. If the graph is simple, the trace of adjacency matrix itself is 0. If I take the second power of adjacency matrix, it means that I consider all paths of length 2. In particular, this might be a path that I go to some neighbor and then return back to my initial node. The trace of a squared equal the double number of edges in the graph. If I take the trace of adjacency matrix in power of k, I have very big number, k in k factorial, times the number of cycles of length k in the graph. So what I'm going, since I don't have time to really work out everything, this looks like a kaleidoscope of different results, but you should be aware then from where we get some conclusions, okay? Now, determinant. Determinant is in fact a scaling factor in the transformation in this dynamical system, a graph or as a dynamical system. It is related to number of permutations available in admissible by the structure of the graph. Okay, so it's quite standard topics. In fact, the determinant always characterize the number of cycles of all lenses available in the graph. Determinant is a kind of a volume, actually. That's what you might learn from previous mathematical courses. Here, this is not a volume, this is number of cycles. Cycles give you volume. You remember spectral drawing of streets of Rome. It has a volume. This is a precise, intuitive understanding of this determinant quantity here, okay? Now we are ready to ask and answer important questions concerning principal invariance of a graph. Graph could be drawn in many different ways. This is on the left and on the right, you have one and the same graph, but they look completely dissimilar, okay? Now, there is a relation between graphs apparently dissimilar, which is known as isomorphism. They are of the same iso, right? So of the same morphism, they have the same form. Despite they look different, we should be able to automatically detect similar graphs, even if they are drawn with respect to different principles. So these similar graphs are called isomorphic to each other. For isomorphic graphs, we always have a relation like that. A1 is the adjacency matrix of one graph, and A2 is the adjacency matrix for another graph which we suppose to be isomorphic, similar to the first one. They are isomorphic if there is a permutation matrix pi capital. Look how it works. So on the left, it acts on the left here and on the right here. So as a result, we have actually a similarity transformation between matrices A1 and A2 by means of matrix pi. Matrix pi, permutation matrix, just somehow shuffles the identity numbers of nodes. Okay, so if we are able to find such a permutation matrix, which makes adjacency matrix of one graph similar to adjacency matrix of another graph, they are isomorphic. If A1 and A2, these two graphs are similar, they have the same characteristic polynomial, the same eigenvalues, the same determinant, trace, and all other graph invariants. We will discuss them later, a little bit later. You see that, but okay, so if I have the same eigenvalues, for instance, for two graphs, it doesn't mean that they are isomorphic. There might be that two different graphs, completely there is no such permutation matrix, but nevertheless, they have the same spectrum. So eigenvalues provide you, only partially they provide you information about the structure of the graph. Now, probably you also heard about earlier characteristic of a graph, as if it's as a kind of invariant or important characteristic. Earlier characteristic of the graph is number of nodes minus number of edges. For the given graph is constant. In fact, this is only one such graph invariant. There are many, actually n graph invariants. So how to calculate them? So for all similar graphs, these graph invariants should hold. So they should have the same value. Okay, so as soon as we have structure, we have set of invariants. Whenever we reshuffle their names of the nodes, the structure of the graph, the invariants of the graph remain the same. So they are major symmetries, so to say, major conserving properties. It appears that if I take a characteristic polynomial of a matrix, characteristic polynomial is used to calculate the eigenvalues. So if I take the determinant of matrix A minus alpha 1, that is, if I take it as 0, right? And I search for some alpha which satisfies this equation, these alpha are called eigenvalues of the matrix. Okay, so these are kind of scaling factors in some particular directions. But if, so what we study in school, we study the left part and we study the right part. Right part 0, left part is determinant. But if I really take, expand this determinant and find this polynomial, I would have, what would I have? I just would have a polynomial with respect to alpha, okay? My potential eigenvalue. And there are some coefficients. These coefficients are principal invariants of any matrix. In particular, if my matrix is a graph matrix or adjacency matrix of the graph, it gives me principal invariance of the graph. As a matter of fact, these principal invariants are some polynomials of number of nodes and cycles of particular length existent in the graph. It might be that two graphs have the same number of triangles, but they are not isomorphic. But if I take certain number of triangles minus certain number of squares minus plus something, you see, it's a kind of some functions of invariance. They should be preserved. This is the core message. So there are some integral of motion, integral of transformation, something which does not change, okay? So there is a way how to calculate these coefficients. People use indeed the generating function for doing that. And in particular, we have the set of these basically invariants of the graph. The first one is the number of nodes. The second one is the squared number of nodes divided by 2 minus number of edges. Then cube number of nodes divided by 3 minus double set of edges times the number of nodes plus 4 times the number of triangles, and so on and so on. Each graph of n nodes has n principal invariants. The last principal invariant is the determinant of the adjacency matrix itself. Total number of all cycles existent in the graph. The first invariant is always the number of nodes. Okay, so that's what you should know that whenever you have a graph, something is fixed there. Some polynomials over the elements, number of elements existent in this graph, okay? Now, there is a special case of isomorphism when graph is isomorphic to its own. It's called automorphism. Automorphism tells you that you might transform somehow a graph matrix or the graph itself, redraw it, and nevertheless, it might look completely different. And nevertheless, it's one and the same graph. So it should have one and the same properties. If the graph, these graphs are the model of particular data set, the data set 1 and data set 2 should have the same property. Probably they have been taken from the same system, but at different times. Okay, so that's what we basically should understand. The example is a Coexter graph, for instance. 28 nodes, 42 edges. It's an example. It has 336 different automorphisms. People are not able to discern them visually, you know, only some trained guys. And this is actually the problem we have. A lot of databases, a lot of graphs are the same, essentially. If I take 28, you know, 28 people, I describe their relations within 42 parameters. Come on. And then I have 336 different modifications for my database, which gives me one of the same, which contains one of the same knowledge essentially. Okay? So graph, big data are mostly redundant. They might contain one of the same information simply because the relation could be described by graphs, and a graph might have many automorphisms. For automorphisms, we have a very nice theorem. If I take a permutation matrix which belongs to the set of graph automorphisms for the given graph, then my similarity transformation should look like the following: that pi permutation matrix and A adjacency matrix of the graph should commute with each other. That means commutator is if I say take AP and then subtract from here PA, it is 0, it should be 0. What does it mean? Well, if you, I'm not sure whether it's studied in the elementary algebra course, but if matrices commute with each other, they have some subset of eigenvectors which are identical. And they commute particularly on this subspace. Okay, so this is the major formula, major theorem for today's lecture. Okay, how much time? Oh, sorry. Yes, so yes, okay, so I will probably, yeah. Now, just have a look, please. We have some some data models, simplexes, graphs, whatever. In these graph models, we consider elements of the database as indistinguishable similar objects. Then they have two types of relationships. First, adjacency. Which guy is adjacent to which one, close to each one. And permutations. We can describe them in many different ways, in principle. Okay? Now, there is something which comes from these two types of operations we may apply to a set of nodes, set of objects. And actually the result is automorphisms, those permutation matrices which are admissible by adjacency. Once you construct a database, a relational database, you establish adjacency. A relational database means that some guy has some property between, team members and their functions, properties. So we establish a relation. This is a relation of adjacency. Okay, they might say that they are good or bad, no matter. There's some relation of adjacency. Another thing is that within these guys, team members, there might be some structure, certainly should be some structure. Okay, and therefore, this structure, based on the relations, or times the relations, it provides us some set of symmetries. In case of a simple graph or Platonic solid, we really see this symmetry. We can turn it and the picture is the same. We can turn it again and the picture is the same. In a real team or in real network, this is not the case because they are not 100% the same. Okay, because, well, simply you could take some function from your friend because he's ill today, but it's not 100%. And we need to have some kind of a more subtle definition of automorphisms, and that is what we generate by random walks. Because it's not 100% correspondence, but only 50% or 3% or 20%. Okay, so this is the major idea for the future. Now, what's going on with all these eigenvectors and eigenvalues if I have an matrix automorphism, automorphism of a graph. Automorphism means that there exists a matrix pi permutation which commutes with A. So if I have an equation for eigenvectors and eigenvalues of my adjacency matrix, I might commute it with pi, and well, and then what's happened? Then I just can say that eigenvectors V and eigenvectors of a commuted matrix should somehow be related to each other. In fact, they should contain the same elements, and I just reshuffle them, and then I have another eigenvector. I don't need to calculate them. And this is mathematically the major mechanisms for dimensionality data reduction here. You see, if you have a huge database, but it has some symmetries, you might use maybe eigenvectors related to these symmetries to dramatically reduce the data dimensionality. And that is how we basically draw quite complex figures like icosahedron, dodecahedron, and other solids. They have many, many nodes, they have many edges, but they are symmetric. So we try to draw them in such a way to highlight these symmetries. Because what people react on, they react on the symmetries. Okay, the interesting that the eigenvectors of automorphically transformed matrix, eigenvalues should be the same. Eigenvectors are changing with those permutation matrices, but eigenvalues are the same. So each eigenvector, permuted eigenvector, belonging to some symmetry of automorphism, characterized by one and the same eigenvalue. It means that there are at least two or even multiple eigenvalues. So how could I understand that there are many symmetries in the graph? I should take its eigenspectrum. If there are multiple eigenvalues, you remember 2 lectures ago, we constructed the distributions of eigenvalues using Maple. And we constructed some histograms. And there are some columns show, I mean, just in histogram, we had some columns, bars showing that there are many multiple eigenvalues. It means that there are symmetries. You remember there were very nice pictures with a lot of cycles. Each cycle gives you an additional eigenvalue of the same additional eigenvalue. So take the spectrum. You might have a multiplicity of eigenvalues. Each multiple eigenvalue describes you some group of symmetries existent in this graph. And some of them might be just few. You see that the graph might have billions of nodes, but there are multiple eigenvalue of dimension 2, of multiplicity 2 or 3. Take it. And then you could efficiently draw this huge database in the dimension of 2 or 3. This is the core, okay, of this algebraic graph theory. Why people do need that? Simply to reduce the dimensionality of the data. Example, this is the very last picture I show you today. So, a low dimensional representation of graph. A Peterson graph, 10 nodes, a regular graph. Each node has 3 neighbors. So I take maximum eigenvalue and so on. So the multiplicity, yes, so the first maximum eigenvalue is 3. It's a Perron-Frobenius eigenvalue. The vector is just, okay, so everything is just 1 over square root of 10 if properly normalized. Next eigenvalue is 1 with multiplicity 4. Okay, it is multiplicity 4. And then, okay, so I can, if I take the matrix of eigenvectors of my edges, of the adjacency matrix of this graph, for instance, if multiplicity 4, I see that each node has 4 coordinates. So in 4-dimensional space, I would draw them properly. Even if, now look, so I'm not in a 4-dimensional space, but nevertheless, I could gain something. I could say that since all my eigenvectors are orthonormal, I have now Euclidean space. So if I want really to calculate a distance between 0.3 and 0.6, I can simply calculate a Euclidean distance between these two vectors. They are orthonormal. They are perfect. And I can really think that I have a situation of Pythagorean theorem. And this distance reflects constructed by, grounded by symmetries. Okay, so this is the principles of visualization and interpretation, in fact, of databases. Interesting question. Why does a cube look like a cube? Why do we draw it like that? So if I take, in my case, a Laplace operator, but it might be also the adjacency matrix of the graph. The spectrum is the same. The multiplicity would be preserved. It just means that I want to use a particular, I take Laplace operator because then I have the clear coordinates, 1, -1, -1, 1, -1, 1. You see, it's just coordinates of my cube. There are also other multiple eigenvalues of order of multiplicity 2. Then I can construct a 2-dimensional representation of cubes. These are on the right-hand side. These are cubes, but they are drawn in 2 dimensions. And this is cube drawn in 3 dimensions because I had a multiplicity 3 for the chosen eigenvalue. So you see the principle. Even if you have a huge database, find some eigenvalue which consider, reasonable multiplicity, 2, 3, 4, low dimensional enough. And then you can reconstruct the data in the Euclidean space of 2 or 3 dimensions. And it helps us to solve many problems. It does not require use of singular value decomposition. It doesn't require use of this non-negative matrix factorization or whatever for clustering or classification. You simply use symmetry. And that is how I believe, that is how our brain is working. It does not calculate any, singular value decomposition or principal component analysis. No, it simply search for symmetries and try to understand whatever complex phenomenon is through symmetries. That's how physics is constructed. And that is what I think that this is a future of all these, well, maybe not future, but nevertheless in the neural networks and related stuff, we don't know how to use this property. We don't know whether there exists a relation between neural network. It's too complicated system. It's a kind of a black box. But in principle, our brain works on symmetries. Symmetries, then you should use a kind of algebraic approach to express this symmetry. So this is what I wanted to tell you today, and then I will, we will continue next time with information, with information properties of how to gain information from these data models, graph data models. Okay, thank you. I stop sharing and stop recording. Thank you so much.